Hi everyone. Today we're going to learn new theorems about proportionality. And this specific theorem is called the side splitter theorem. And you'll understand why it's called side splitter once we go through it. So a side splitter theorem has to do with what's called nested triangles. So nested triangles, and I'll even write this down because it's important to remember this word when I say it. Nested triangles are triangles that are like inside one another. So this smaller triangle here is nested within the bigger triangle here. So like the formal definition of nested would be the vertices lie on the sides of the bigger triangle or whatever. But you can really just remember nested triangles as triangles that are within one another or inside of one another. However you remember it, you write that down. Okay, so side splitter theorem has to do with these nested triangles, and it talks about different proportions within the triangles, essentially. So the reason we're talking about side splitter theorem is because it has to do with similar triangles. Now, these may not necessarily look similar, but let's kind of unpack why those are similar, and then we'll get to the actual theorem. So you have two triangles here. Here's one triangle, is the bigger triangle, and the other triangle's inside of that. So hopefully you see those like two triangles there. And they're nested inside of one another, but these are similar. And the reason they're similar, or the reason we know they're similar, is because of these lines and the symbols on those lines right there. What do those arrows mean? Those arrows are denoting that these lines are parallel. Okay, so this is going to go back to when we talked about parallel lines cut by transversal. If I extend these, it looks a little bit more familiar. So we have two parallel lines, and these parallel lines are being cut by a couple transversals. Here's one of them. And we know that a bunch of angles are congruent because of that. One of the angles are corresponding angles, which are angles that are in the same position. So for example, if I take a look at this angle here, this is on the top of the parallel line to the right of the transversal. The one that's on top of this parallel line to the right of this transversal is congruent to that angle because these are corresponding angles. I'm going to write that down. These red angles are corresponding. This is a review of Unit 3, I think it was. Those are corresponding angles, so they're congruent. Okay, if you use our other transversal, so this is also a transversal, if you kind of like take away the triangle part, we have another set of corresponding angles. So this angle's on the top left of the line, on the top left of these two lines, so the top of the parallel line, left of the transversal, those are another set of corresponding angles, and they're congruent as well. So with that, you kind of see that these two triangles, the bigger one and the smaller one, have similar angles. So I can even separate those if it's a little bit easier to see. And I have this triangle here, and if I redraw that, it looks like this. Maybe not, close enough. So you have side A and side C, and I have this one marked here and this one. Okay, that's a smaller triangle. Then the bigger triangle here, okay, would be a combination of A and B and C and D. And I know that these angles are congruent to the ones in the smaller triangle. So this angle is congruent to this angle is congruent to this. By process of knowing that all triangle angles add up to 180, this angle has to be congruent to this angle as well, which is this angle on the big picture here, which makes sense because the triangles have a shared angle, which by reflexive property has to be congruent to itself. Both of this triangle and this triangle have that angle, so obviously that angle is congruent on the pictures when I separate them. Okay, so since all the angles are the same, we know these are similar triangles, because similar triangles are triangles that have the same shape but different sizes. So all angles being the same implies, I'm going to draw an arrow to mean implies, that the triangles are similar. Okay, if you have a question about that, now would be a good time to pause, raise your hand, and ask. Otherwise, I'm just kind of showing you that these two nested triangles are similar. Okay, with all that information now, I can talk about what's called the side splitter theorem. The side splitter theorem has to do with those nested triangles, and it has to do with similarity. So similar triangles are nested triangles. Okay, so the theorem says if this picture, then this ratio. Now this isn't a formal way of saying it, so I'm going to be more specific. The part we're looking about in this picture is if the two lines are parallel. So I'm going to write that out here. Where should I write it? I'll write it out here. So if the bases of the nested triangles are parallel, or if two sides of the nested triangles are parallel, And I'm going to use the symbol to denote parallel. It looks like parallel lines. So if parallel lines here, then this ratio is true. So the ratio is A over B equals C over D. Okay, this ratio, or this theorem really does make sense if you think about it. It comes from just comparing similar triangles in general. I will talk about it more after the video. But just know for now, if nested triangles have parallel lines like this, so one side of a triangle is parallel to another side of a triangle that's nested in one another, then the ratio of A over B, so like the side of the triangle, to like this little piece of the bigger triangle, so it's a piece of the bigger triangle, is the same as a scale from this side of the triangle to this little piece over here. Okay, there's many examples we can use, including just, finding straight lengths of segments. So you know in the diagram that QS is parallel to UT. It says it in the arrows and it says it in the statement. You know all these side lengths, and it wants you to find the length of RQ. So you can straight up use side splitter. That would be method 1. Side splitter theorem. And it's called side splitter because this parallel line splits the side. If you think about it, it makes sense. So side splitter, I would just say, okay, if I know these lines are parallel, then the ratio of this to this is the same as the ratio of this to this. It'd be that easy. So maybe instead of calling it question mark, I'll call that side RQ. The ratio of RQ to QU, which is 9, would have to equal the ratio of this to this. So it'd have to be the side of the triangle to like that part that's part of the side of the bigger triangle. And then I can cross multiply and solve. If you don't want to call this RQ, you can call it X, you can call it Y, you can call it Q, you can call it whatever you want. It makes it easier to cross multiply, that's fine. So you'll multiply here and here. So 6 times X is 6X. Set it equal to 4 times 9, which is 36. Divide both sides by 6. You get X equals 36 divided by 6 is 6. Okay, so that represented the length of the side. So 6 over 9 is proportionate to 4 over 6. Or, method 2, you could technically go with, just what you've learned about scale factors. And let me show you how that would work and how side splitter makes sense. And I'm going to call this X for this. So method 2, I've kind of already taught you. You can draw these as triangles that are split up. So the smaller triangle is QRS, where QR is X, RS is 4. Okay. And then the bigger triangle is URT. I'm going to draw those with corresponding parts in the same place. And let's see, UR now would be this whole side. I don't know the length of that, but I know it's got to be 9 plus whatever X is. Or you can call it X plus 9, it doesn't matter. RT is this whole side, so 4 and 6 gives me 10. And you can set up similar triangles and set up a proportion how you learned in previous videos and discussions. So I know that this side is proportionate to this side. So the smaller triangle to the bigger triangle will be X over X plus 9. I know that this side is proportionate to this side. So 4 over 10, that scale factor, if I divide those, has to be the same as the scale factor to go to between these two sides. Okay, you can do it the other way too. I could do 10 over 4 equals X plus 9 over X. It doesn't matter. And you can solve it this way. And the reason that side splitter is nice is because I don't have any equations necessarily. I didn't have to think about how to set this up. I could just use the theorem, pretty straightforward, X over 9, 4 over 6. This one took a little bit of splitting up the triangles, then figuring out what the lengths of the sides of the bigger triangle are, which isn't hard necessarily, it's just extra steps. And I don't care which method you use, you pick whichever one works for you better. So if you just like this over this equals this over this, that's fine. But I like method 2 because, the computation is not necessarily easier, but it makes a lot of sense. The scale factors are being set equal. That's what we've been doing all along. So you choose which you like. And then all you have to do is cross multiply. And you should get the same thing, which proves that side splitter works. So I'll have to do 10 times X. Is 10x, and I'll have to multiply 4 by X plus 9, and this is where I see a lot of algebraic mistakes happen. You're multiplying all of 4 by all of X plus 9, so you'll need to distribute that 4. So we'll get 10x equals 4x plus 36. Okay, subtract the 4x so you can combine those x terms there. So 10x minus 4x, and I'm going to move this up here because I ran out of room. 10x minus 4x gives us 6x equals 36. Divide both sides by 6. Look, you wind up getting the exact same thing. So I don't care if you use method 1, which is side splitter, which is pretty easy, straight up computation, but you have to know the theorem. Or you can choose to use method 2, which is what we've been doing all along, set up the two similar triangles, figure out that they're scale copies of one another, set up the scale factors. Scale factors would be equal because all sides are scaled the same. Like, this is what you already know. Just sometimes the algebra might be a little bit more difficult if you're given the side splitter information. You choose what you like. Okay, example 2 is kind of going with the converse of side splitter theorem, which I wrote in your note sheet but I haven't talked about, so kind of just take a look at that. The converse is also true of the side splitter theorem. And converse is another way, I guess the best way I can think of it is the reverse. So going forwards with side splitter, it says if parallel lines, then the ratios are equal. It also works in reverse. So I could say if the ratios are the same, then the lines are parallel, right? I'm going backwards. It works both ways, which I wrote here. If the ratios are equal, then the bases of the similar triangles must be parallel. It doesn't necessarily have to be bases, but like the sides of the similar triangle. So if this is true, then parallel is true. So I can determine whether or not MP, which is right here, is parallel to LQ. And I probably don't even want to mark that because that's questionable, but I'll draw a question mark next to it. Okay, so in order for those to be parallel, the ratio of this to this would have to be the same as the ratio of this to this. So the ratio of 24 to 12, well, what's 24 divided by 12? It gives me 2. Is the ratio of 8 to 4 also 2? Well, what's 8 divided by 4? Is that 2? Yes, it is. So I would say yes, it is. I would want to show my calculations, but I always want to give a reason and be able to explain it. So my reason is the ratios are equal by side splitter. Side splitter theorem. I don't know, I should write it that way. You can write it out on your own paper. But that's another application of side splitter. And one more example is just kind of looking about which ratios are possible, or which side lengths are possible. So you have to think about, like, okay, the ratio of this to this is 4 over 6. Which ratios of these two sides would be equal? And I'm going to leave example 3 for you to try and think through on your own. So that's all about side splitter theorem. It's basically just another application of similarity if you think about it. Method 2 you've already learned, but method 1 is another tool you can add to your toolbox. If you have any questions, please ask now. Otherwise, try example 3 on your own.